Kent has been in 7 countries in the last 4 months, but has joined us here tonight to talk about Ethereum, the world computer. Take it away.
Hello. Can you hear me? OK, this works. All right, so first, a big thanks to all the Papers We Love organizers, Zishan, David, Darren, Lydia. So they do an awesome job, and this is my favorite meetup, so just throwing that out there. OK, so today I'm Libby. I've worked in blockchain, cloud, different things, so I'm a programmer, whatever. So this is, I'm going to present the Ethereum white paper that was written in 2013, so that's like about 5 years after the Bitcoin network went live, written by Vitalik, who was at that time 18, I think. And so it's the world computer, or sort of a fabric for running smart contracts. So the overview I'm going to do is a big section of this paper sort of covers Bitcoin and the proof of work blockchain. So I'm going to go over that first to make sure we're all on the same page and we can get that. And then we'll talk about when they enter, like with Ethereum, and the idea of sort of generalizing this blockchain and providing sort of a decentralized consensus platform that you can write general purpose programming languages on and also control arbitrary state transitions. And then we'll talk about the EVM, which they mentioned, the Ethereum virtual machine. And finally, dApps, or distributed applications, and smart contracts. That's kind of the overview. So I mentioned in the paper that at this time of the writing, Bitcoin had been sort of proven out in the wild for about 5 years, and it was sort of 2 parts. So one is a peer-to-peer online currency that maintains a value irrespective of any intrinsic value or central issuer. And he mentions that there had been many digital currencies before in the 80s and the 90s, but they sort of all had this problem of they relied on some central issuer or something to keep track of the state of who owns what. So there was DigiCash, and there were other solutions, but Bitcoin had the second part, which is the novel sort of proof-of-work-based blockchain that allowed you to have a decentralized system where you could still come on public agreement about the state of the world, right? So in sort of currencies, you need this first to file, which I talk about in the paper, which is basically if I have $5 and it's represented as a token, I can't spend it with Leanne and then go spend it with Tom, right? If I spend it with Leanne, it has to be recorded first that that happened, and then I no longer have that $5. So you need to have some way to come up with a global state of the world and some order of transactions. So the state of the world we're trying to keep track of in Bitcoin is who owns what, a public ledger, right? So these people own some amount of Bitcoins, or whatever your value is. And if you had a centralized system, this would be easy to do, right? Because you have one node, and all the transaction would go through that node. So the order that that leader sees it, or that order that that central system sees it, is the order that you're going to distribute to the rest of the nodes and say, like, this is the state of the system, right? So Zishan gives 1 to Scruffy, Drun gives 1 to Scruffy, and everyone sees that as an order of transactions. So we can imagine here we have sort of like the start state, where we're starting. Let's see if this pointer works. Yeah. OK. And then you have just all the same leader just accepting transactions one at a time and updating the state of the world. So your state of the world is just what you get by applying each transaction one after the other. So here you just have the person that owns the currency, Zishan owns 1, and is sending it to Scruffy. So that would take 1 away from Zishan and give 1 to Scruffy, right? So another one comes in that updates the state of the world. Well, this is good because it's all centralized. But what if we want a world where, like, we can have anybody join? So now you have different peers coming into the system, and they all potentially have the right to commit the transactions that they know about. This is a difficult problem and hadn't been solved before Bitcoin. It had been talked about, they say in the paper, like there's a Bcash paper and some other things, but it had never been proven out. So now you have arbitrary people coming in, so you don't know the number of nodes that you have in the network, right? They do mention that there had been research in something called PBFT, or partial Byzantine fault tolerant algorithms. But in those situations, you need to know the participants that are there. You need to know I have 5 nodes, and these are their identities. What you can do in this decentralized world is just have everybody in this room could just join and leave. There could be 1 node in the system, or there could be 1,000 nodes, and they're coming at different times. But you still have to be able to say everyone's going to eventually, probabilistically, see the same view of the world. Well, let's see if that's right. So what happens there is you have all the nodes listening. You have a start state, just like we had before. In blockchain world, it's called the genesis state. and that's block 0. And then after that, all the nodes listen for transactions. And they'll be getting transactions, and then they'll be putting them in a tree. So we could all be nodes here, and we could all be getting transactions. And then every now and again, you're going to sort of get this leader selection, and someone's going to come up and say, it's my turn to commit those transactions that I know about. And they'll get the right to do that, and then that will be what everybody else will accept. And someone else will come in and say, no, now it's my turn to get that. So these are the transactions I know about. And they'll be able to share that with the rest of the nodes, and it goes on, right? So it's not deterministic, but it kind of gives you this like probabilistic round robin where people get the ability, or peers get the ability to actually participate by committing what they know. That makes sense so far? Yeah. Okay. So the way to do this is with something called proof of work. And that's what they say is the way that the peers gain the right to participate in the system. So that's also called mining when you talk about it in Bitcoin or Ethereum. And so what miners are doing, what proof of work is something that's hard to find a solution to, but easy to verify. So I sometimes think of it like a boggle, like a travel boggle game that you have that you'd be shaking. And you could make it like, so at the top you just want all A's. So everyone here could be shaking that. And as soon as they get all A's across the top, they could raise their hand and say, I have the A's. And we could all go over and look at it, and we could verify very quickly that they do have the A's. And proof of work actually comes out of a concept that they mentioned in the paper as well from Adam Back, where they were using it for hashcash, which is a way to deter spam. So the idea there is if you're trying to spam someone, you're going to send out millions of emails. And you're going to hope that like one person bites, right? So one person is going to send 100 Bitcoins to the Prince of McDonald's at this address, right? But if you make it hard so that they have to pay pennies to send that email, that's going to deter a lot of people from just sending out millions of emails. So that was sort of the initial idea of proof of work. And then that was used to apply to Bitcoin. We'll see in a second how they do that to achieve this decentralized kind of consensus. OK, so we need to just refresh on what a hash function is, because this is the puzzle that we're going to use for this proof of work. And David gave a good talk in December on hash and SHA-256, actually. So if you want the gritty details of how to do a hash function, go watch that lightning talk from December. But basically what you need to know is that a hash function takes any size input and hashes it down or reduces it down to a fixed output. In this case, 256 zeros and ones, right? It has the properties that it's pseudo-random, so you can't guess the output based on the input. It's not reversible, so if you have that output, you can't guess the input. And it's deterministic, so if you put the same value into the hash, you're going to get the same output. So we can use this for a proof of work. And how do we do that? OK, so now we have all the nodes in the network mining. So they're sitting there, they're collecting transactions that they hear about. So we can submit transactions to any node. They put them in a tree. And at the same time, they're generating this nonce, or this value. And they're taking that nonce, and they're concatenating it onto the header, the block header that they know about. And then they're running it through this SHA function. And they're trying to hit some sort of target. So that target could be, it's configurable, and this is actually important because it sets the difficulty for how often you can win the right to commit. So in this example, we're saying they have to hit 6 zeros. So they could run it through once, they could hit just 1 zero, that wouldn't count. They run it through again, maybe they get 3 zeros and some whatever afterwards. So it's like called partial hash inversion. But the point is basically you just try to hit that 6 zeros. And that again will figure out the difficulty of like how hard it is to do. If it was only that you had to hit 1 zero, you'd have a 50% chance to get it, right? And then 2 zeros, it's going to go up by, no, it's a 25% chance. So every time it's 2 to the number of zeros, 1 divided by 2 to the number of zeros. So Bitcoin wants to make it so that on average, it takes 10 minutes to mine a block. So they'll rejig that difficulty parameter every 2016 blocks to make sure that on average people are just winning this every 10 minutes. So once you win this nonce, so this miner found the nonce, they get the chance to commit. They get the chance to say, this is the state of the world, right? So now they come in, now they're like that leader, and everyone should listen to them. So they'll take all the transactions they know about, and they'll send them all around, and they'll send that nonce that they found around to everybody, and people can verify. They can take that nonce, and they can take the header from the block that they're working on. They can run it through that same function and make sure that it hits that target. If it does, that's okay, and if the transactions they gave are valid, it's okay. They'll accept it, that's the new state of the world. And that miner will get some of this lovely, lovely Bitcoin here for doing that. So they'll mint some more Bitcoin, and then that sort of pays them for doing the computation, for spending their resources to do that. There's one other part to this, which is there could be a tie, right? So you could get the point where two people found valid nonces, even though there could be different nonces, but they're still hitting that target. So then you have what's called a fork, or like kind of split brain in database world or whatever. And the rules of the protocol say, well, you always have to mine off the longest chain that you know about. So you could have this where you have for a while, part of the miners or part of the people are listening to this is the state of the world, and the other part are listening to this is the state of the world. But eventually, someone will win on one of the chains, and that will become longer. So this one will become orphaned, or will become ignored. And people will move to the other one, and then they'll converge. So that'll be the state of the world. So that's how it deals with forks. Great. Okay, so what do these peers look like in Bitcoin? So they talk about, so each peer, or each node, has its own local copy of state. And again, state in Bitcoin is just who owns what, that ledger. And there's going to be a Bitcoin talk later, so they'll go into detail about how you actually look this up. But they're basically called UTXOs, or unspent transactions. So you need to be able to reference that. You have a tree of the transactions that you know about and the new ones that you're hearing about. And then there's network protocol rules. So for Bitcoin, it's like each block can only be 1 megabyte. You have a block time that's on average 10 minutes. That's what we just talked about, where you reconfigure that if it's not true every 2016 blocks. And it uses this consensus mechanism called proof of work. Cool. So the state in Bitcoin is, again, these counts. They're just associated with private public key pairs. So your public key is inside of the system, but your secret key would live outside of the system. And that's only used to verify that you actually are the owner of that account. So just a quick refresh on what a digital signature is. That's if you have a private key, you can sign with that private key. And everyone else can verify it with the public key, right? So this is how you'd send a transaction. To make sure that you know that you own it, or that everyone knows that you own it, you can sign it with your secret key, and then they can check it out. So the paper's like, okay, so Bitcoin's basically like the state transition system, where you have some state, and the state is who owns what Bitcoin. And then you have these transitions, which are, I'm going to transfer some amount of value from account A to account B. So that's just your little transition function, state, and then some transaction, and then you get your state prime. Great. One other thing just to quickly mention that talk about is Bitcoin does have a scripting language. It's not what you call Turing complete, so just meaning it does not have loops. It just has a bunch of opcodes. And the most trivial opcode is what we just talked about right there, is verifying a signature, or verifying that this private key is associated with this public key account, right? Stack-based language, great. So quickly after Bitcoin became live, people started doing these alternative applications on top of Bitcoin. So I mentioned Namecoin, which was a whole fork of the protocol. So you fork Bitcoin, you deploy your own network, you run all your own nodes, and you use it for a different reason. Namecoin is a DNS system for decentralized DNS. That's kind of heavy. And another alternative application they mentioned is colored coins. So now instead of just a regular Bitcoin, you can add some data to a coin, and from that point on, it will have a special meaning. So we could make like a PapersWeLove coin, but we'd have to put some special data in there, and I don't know what that would represent, but it could represent something, right? And there's over 1,000, like 1,000 of these different things, probably way more by now. And the other way you could have one of these applications on top of this decentralized consensus blockchain would be metacoins, and that's a protocol layer that lives above blockchain but utilizes the mining and the networking that we talked about before, right? So of course there's like peer-to-peer networking, node discovery, and all this other stuff that goes into deploying one of these networks, right? So people want to leverage that and do different things on top of it. So the paper says, great, there's these two approaches. There's you build your own independent network, you deploy it, you make sure it's safe, you check it, that's a lot of overhead, right? Or you build a protocol on top of Bitcoin, which also is not the easiest thing to do, right? You have these color coins, you can sort of do something in there, or you have this metacoin thing where you're watching the network, but if something bad happens, you can't really control it, I don't know. So it's pretty heavy-handed. So they say like you have to bootstrap yourself to do this, and for a lot of developers, we just don't have the time. We have day jobs, we have other things. Like it's hard to be creative if you have to do all those types of things. So the idea is kind of blockchain as a service, or why don't we just take blockchain and give people this platform plus a general purpose programming language plus arbitrary state so that they run that network once, and now they can deploy this code into it, and they can take advantage of this huge network that's running, that's already proven to be safe and, or tested, or I'm just kidding. Anyways, so that's the idea. Let's give people the power to deploy to this blockchain. So, I don't know. I'm supposed to talk that fast, or I don't know. I can. I'm trying to slow down a lot, and if I talk too fast, please let me know, because I tend to do that. So Ethereum is the cryptocurrency that's generated inside of, or Ether is a cryptocurrency that's generated inside Ethereum. And it's the main fuel, so it's used to pay miners, like we saw in Bitcoin. And it's also used to pay transaction fees, which we'll talk about more in detail in a second. So Ethereum now has two types of accounts, they say. We're not just going to have these external accounts that are very similar to Bitcoin, but we have external accounts and internal accounts. These external accounts, they're similar to Bitcoin in that they are associated with a private key, which exists, or a secret key that exists outside of this closed Ethereum world. And you send a message by signing that transaction and sending it into the system. So these are your external accounts. And now you also have these contract accounts, or these internal accounts. And this is contract code that's deployed at some address, but it just sits there dormant, just sleeping, until you actually invoke it. You send a message to it, and that'll wake it up. And once it's woken up, it can read and write to storage. It can create other contracts. It can call messages out. It can do all sorts of things once it's woken up, but it won't wake up by itself. Kind of like lambdas, in a way, if you think about it. Like lambdas plus storage, that's associated with it, maybe? I don't know. OK. But so then you have Ethereum accounts. That's the state that we were talking about before, much like the ledger was a state, or just who owns what Bitcoin and Bitcoin. And the state transitions now are transitions of value, so you can transfer value from one entity to another, or you can transfer information from different places and things. Yeah. So those are state transitions. And an account looks like this. So account has an Ether balance. It has a nonce. This is used for to prevent against replay attacks, and so you know which time this thing is being invoked. And optionally, it has these two different things, contract code and storage, which are set only if it's one of those internal accounts or one of those contract accounts. So they're null by default or empty by default, but they're there. I kind of meant to remove this slide, but this would just show you, so here's an account address, and at the bottom you have your account information, and if it's a contract account, you'd have a pointer to a tree of your state. Okay, so how do you interact with the system? Right, we have these different accounts in there. We have this consensus mechanism running. Great. What do? Well, there's two ways to interact with the system. One is transactions, and one is messages. And transactions are coming from external accounts. So this is the way that you sort of wake the system up, right? You can only wake the system up by having a private key and sending a transaction into it. So you sign a data package, and you send it in. And messages are sent from external or internal accounts, and they can just go around and spawn other things, and they're basically function calls, because they return values, they do all this. So these are the two ways to interact with the system. So here we have our little panda. He's starting a little transaction. So he has a private key, which he signs a transaction with. But once it goes into the system, it can hit a contract, wake it up. This contract can do a thing. It can save some state. It can send it out to another contract, which can do something, save some state, which can go to another contract, which can go to another contract, which could go forever, right? So this is a problem. So that's why they had to introduce this thing called gas, because we have this thing in programming languages called halting problem. We don't know if it's going to terminate. Well, in this one, we do know it's going to terminate, but generally, we don't know it's going to terminate. So how can you get around that problem? We can't look at the code and determine whether it will actually stop or not. So we say, you got to actually tell us how many computation steps you think your transaction is going to take. And that's where the concept of gas comes in. You have to pay a little bit of this intrinsic value or this cryptocurrency stuff to the process in order to get it to execute, to the miners to get them to execute it. So gas has two parts to it, as I mentioned. There's a start gas, and that's the amount of computation steps you think that your transaction is going to take, right? And then there's the gas price, which is how much are you willing to pay per step in your process, right? So in the example they show in the paper, they say, here we have a start gas of 2,000, and we're going to pay 1/100th of an ether every time. So to get the maximum value that you're going to spend for that transaction, you multiply your start gas by your gas price, and you have 2 ether, right? So what will happen is when a miner gets this transaction, this signed transaction, they'll check that account that sent it, see that you have enough money or ether or whatever in your account. They'll debit that from your account while they're running it, and they'll start running the transaction. So each step is going to be worth a little bit of gas. If you run out of gas and you didn't complete your transaction, the transaction is canceled. All your state's wiped out, you're sent back, but you don't get your gas back, right? So I mean, so like that's part of it. So you can set that high, but it stops the thing from somebody saying, okay, I want to have like 1 billion start gas and I want to pay 0.0001 for it and spamming the system. The miners can also decide not to accept that, right? Because that might be a little weird. But yeah, that's just one way to do it. So what you have in a transaction is it looks like this. You have an amount of ether that you're sending. So if you're just doing a value transfer, I'm just transferring some ether to Brian, then I would just have an amount here to Brian, and I'd sign it. But if you're doing a contract call, you'd also add this data, and then you have this start gas and this gas price, and the nuts. So that's a transaction. And how does this code actually get executed? So if we're talking about this contract code and stuff like that, how does this actually get executed in Ethereum? And that's where they bring up the concept of the EVM that supports a Turing-complete language or allows loops. So it's called the Ethereum virtual machine, kind of like the JVM. But every peer runs its own instance of the EVM, so it can execute these instructions. And you are going to write in a high-level language, so you wouldn't write in EVM bytecode, but you'd write in some high-level language. Right now, that would be Solidity. At the time of writing it, I think they mentioned Serpent. But it would compile down to EVM bytecode, and that's what you would submit to the system. And the EVM has access to some things. It has access to the block state. So that would be like, what number block are you at? What was the nonce that was generated? So they mentioned sometimes you could maybe use that nonce as a sense of randomness. Okay? And then there's transactions, there's messages, there's code, there's volatile memory that's going to get allocated as you're executing things. There's the stack, it's a stack-based language, and there's a program counter, and there's gas. So when we go to initialize the JVM, we'd have this program counter at 0, we have a stack that doesn't have anything on, we don't have any memory, and we don't have anything in storage. But we sign a transaction, and we send something over to it. And just go through the 2 instructions that they talk about in the paper. It's like add. So this is what it might look like if you have the actual bytecode of the EVM, right? You have your program counter here. It points to some instruction. You have your stack that's actually doing the execution. So for add, the rules are you pop the top 2 off the stack, you add them together, and you push them back on. And then each operation is worth some amount of gas. So paper mentions add is worth 1 gas price, whatever you had set your gas to, right? So you'd minus 1 gas from your start gas, and then you'd increment that program counter. Another operation that they talk about is the S store. So in this instance, you have this S store. It's pointing to some, the program counter is pointing to that. It will take the top one out. It'll insert that into your contract storage. So the second item on the stack gets inserted into the 0 index of your contract storage. And that's more expensive. So they say that one's 200 gas, right? So you have to be aware of like how much each operation costs when you're actually submitting things to the EVM. This is kind of like a debug tool, so I just thought this is kind of neat. So DAPUB is a company that makes like tools for developing on Ethereum that I really like. And so you could run your code, your Solidity code, and you could compile it, and then you could debug it with this. So this is just basically showing, this is all the EVM bytecode instructions, and this is the stack, and this is all the gas. It's a lot of gas. but it's just a test, so I don't have that. But what it's saying is right here is like, okay, push 1 on top of the stack here, right? So then 1 goes on top of the stack. It says push 0 on top of the stack. The 0 goes on top of the stack. And at each step, it's going to decrement your gas to make sure that it will eventually stop. It says load, so whatever's at index 0 in your storage, load it onto the top of the stack. So that's 1. Add those together, so pop the 2 off the top, add 2, push on 0. Duplicate the second element on the stack, so 2 now will go on the top of the stack. Swap 1 and 2. Take that top index, store it in the storage, or store number 2 in index 0. Bam, pop that 2 off the stack, and jump. So now you're going to jump back to some spot. And this jump is what allows you to do these loops, right? Because you could just say jump back here, jump back here, jump back here. And you could get into this infinite recursion. But because you have gas, that's not allowed. So this is what Ethereum basically gives you, right? It abstracts this idea of the blockchain, this decentralized consensus mechanism, says don't worry about that. Don't run your own network. We'll take care of that. Maybe we'll even change the decentralized consensus mechanism. Don't worry about it. Then we'll give you this code execution environment that you can run some code on. We'll take care of the state for you as well, so you have some state. And you can now write in a high-level language something that looks kind of like Python or JavaScript or whatever, compile it down to the EVM code, submit it, and now you can become creative and just run any of these decentralized applications on this already provided blockchain. That's pretty cool, I think, because it really reduces the overhead of what you have to do. So we could just write a little application right now that could be like, okay, everyone that RSVPs to a meetup, they have to put a little bit of Ether in something, and this is called a smart contract. And if they show up, they get that back. But if they don't, then it goes to beer fund, right? So these are called smart contracts. And they also mentioned the fact that smart contracts had been around for a while and talked about in 2005 by Nick Szabos, who mentioned them and had the idea that you're interacting with code all the time. Like when you put $2 into a vending machine, you're expecting to get some water out or some Coke out or whatever, and that happens. So we could make these smart contracts, but in 2005, there wasn't the decentralized databases that existed in order to make these things a reality. So now we can kind of do those. Then the paper sort of goes on to talk about a lot of different applications that you can run these on. The first one is, obvious one, is tokens, or just making your own types of currencies. So we could have, again, these PapersWeLove tokens, and in Ethereum, that would be relatively simple to make. So it's kind of like Ethereum 101 to make your own token. I wanted to make one for tonight, but didn't quite get there. I'll make one to the weekend, and I'll give it to Zishan. Zishan can give them out to everybody. And the other one is financial derivatives. So I don't know if this is too much, but in the paper, he's talking about sort of a hedging contract. So you have the underlying asset of Ethereum or Bitcoin, which is very volatile and changes all the time, as we know. In the news, it's good, it's bad, it's whatever. So if you had a contract, you could say, okay, we want to enter into a contract, and party A and party B are going to put $100 worth of Ethereum into this contract at timestamp 0, right? And then in 1 week, party A is going to be able to extract $100 worth of Ethereum. It could be a totally different amount, right? Because the price could fluctuate so much. So how could you do this? Well, you would write a contract, but you'd still need the idea of what's the conversion, right? What is $1 to Ethereum, Ether? How do you get that? So they talk about the idea of an Oracle contract. And an Oracle contract would be a contract that sits there that you could send a ticker into and say, from the outside world, because remember it's a closed system, so everything's basically deterministic, but you still want to be able to get outside information into it. So you could have the NASDAQ send a little ticker in every minute or whatever and update the value. And then other contracts could query that Oracle, because now that would be inside of the closed system, and say, hey, what's the exchange rate right now? That's an example of a financial derivative, and then you could have a contract like this. So I mentioned that. Vitalik mentioned stable coins, and Maker is one that I like too. Same people that make DAppWeb, actually. Awesome group. So stable value coins are things that you could actually use. So like Ethereum is so volatile, Bitcoin's so volatile, so people aren't necessarily using it as a currency because they're like hoarding it or they're trading it or whatever they're doing. But if you had a stable coin that was like softly pegged at $1, people would be more apt to spend it because $1 today is $1 in a week, more or less, right? So Maker is one of those. Another semi-financial applications would be like UBI, or Universal Basic Income, and Circle is something that works on that now. So I think it's kind of cool that he mentioned all these things in the paper, and now they're sort of happening, like in a way, or people are at least trying them out, right? Let's see if they work, but I think that's very cool. And so non-financial applications that he mentions are things like identity and reputation systems. So you have Uport doing something on that, and he mentions Namecoin is kind of like that, or that DNS thing that we mentioned before, right, where you have to register yourself with some decentralized domain. Decentralized file stores like IPFS, and then decentralized autonomous organizations. He spends a lot of time talking about that, which would be basically if you wanted to have some sort of company or something, you could set up all these contracts, or some organization. You'd set up contracts that would have rules in them that would say, oh, we're going to pay everybody X amount of dollars, everyone's going to get this much time off, we can vote in somebody if 67% of the people say you can join, and this is all written down in the code. Or we can change the rules if 67% of the people say change the rules. So he talks about, although these contracts are immutable, there would be ways to set it up so that you could change out the calling code inside of the contract. So then you could have this organization that's run just based on the code and see how that goes. And then there's things like CryptoKitties that came out that didn't write about, but they're there. This is kind of a tangent. I don't know if I should go over this one. I'll skip this one. So the cool thing about Ethereum, I think, is that you can, like, it does simplify it for developers and sort of leverages this idea of creativity, where you can now create anything, not anything, but like you can create these smart contracts, deploy them, and just try it out and see if it works. Maybe it works, maybe it doesn't. Maybe somebody's like, maybe that should be a centralized system, it'd work much better. Yeah, maybe, but maybe it's also working as a decentralized system. But it gives you this ability to play and just try it out with relatively low overhead. Yeah, it's easy to create alternative coins. I will make a PapersWeLove token. I'm really sorry I didn't get to that. So I sort of think it's fun that they're touching on like really, really deep, like hard problems, but also playing with it at the same time. So I put a picture of Charlie Chaplin there because I love Charlie Chaplin. And I think what he does is he's always having fun, but he's touching on like really deep issues of poverty and hunger and this other type of thing. So I think like if you can try to play around with ideas and not take yourself too seriously, but also try to keep your ethics and make sure that you're focused on the right things, that we can create cool things. And that's why I really like the paper, because it's more like empowering people and trying to say, let's try this out and let's do it. And then since 2013, now we're 2018, and it's running. There's lots of nodes all over. We can all go home this weekend and write something and put it out there and just try out an idea.
Questions? Yes, we have lots of questions. Let's start over here.
So if you're not the miner that wins the block,
Yep.
And you're not going to get the gas cost, why actually run the smart contract? Like, so what keeps these smart contracts actually consistent, like, over time? Like, it doesn't seem like you have any incentive to update. You know, if one person wins the block and says like, oh, these transactions are going into the block and they're going to mutate the state of like all these different smart contracts. Like, if I'm not getting paid to run it, like, why don't I just skip those?
Because you want to get paid maybe later, right? So you'd have to have the updated state. You'd have to become part of the network so that you're on the most current block, so that then you have a chance to win the next one. Otherwise, you'd be mining on a block that's behind.
So in order to so I can't just take the like the hash of the last block and like start mining off of that without having actually run all of the smart contract code?
Without having to run it. You mean?
Like if I know the last hash, I can start mining, right? I think.
Well, so you have the header, right? So you have to have the hash of the header, so you have to have all the state, and part of it's that you have to accept the block only if it's valid.
Okay.
So another part of it is you need to check all the transactions to make sure they're valid, right? To make sure that that person did actually own that. Otherwise, you'd have an invalid block, and you might be mining on an invalid block, so then you would be in the minority, so you would lose. You'd fall behind. Does that make sense? Because
Yes.
you have to check the value of all the transactions that you got as well to make sure that you pointed to some valid state.
So there's some like output that gets in the hash.
Yeah, And you want to make sure that you're not just accepting an arbitrary, like that's part of the acceptance protocol, right? Otherwise you're just accepting an arbitrary hash and you don't know. So the other step of accepting it is validating all the transactions as well.
Thanks.
Yep.
Who governs computational complexity in the network, and is it immutable, or it has to be propagated across the network if it changes?
Computational you mean the difficulty?
Yeah.
So like how do they jigger that difficulty thing that happens every 10 minutes?
Yes.
So there's a timestamp in the header actually, so they can see on average like how often a block is created, and then every 2016, that's what the protocol says, they'll just check it. I'm not exactly sure where it's stored, but they'll check it to make sure that on average it has been 10 minutes, and then they can have a protocol that's like in the code. No one person is looking at it, and it's governed by the code. I think
So it's constantly revising it.
Yeah.
Okay.
And it's not on a time, but on like a number of blocks, right?
Okay. All right. Thanks.
So every node would be able to figure it out.
Yeah, every node, just as part of the protocol. If you're running the Bitcoin protocol as it is, then you do it every 10 seconds. So this is where I was going to show this one, where Ethereum actually does it slightly different. So it's not every 10 minutes, it's every 10 to 15, oops, sorry. 10, I'm just like shooting people in the eyes. Okay. but in Ethereum, it's actually every 10 to 15 seconds that they do it, right? But that brings some other issues.
Yeah. Storing is pricey because you're presumably adding load to the state.
Yeah.
Is like removal really cheap, or do you get some gas back?
You mean like if you're like, oh, I want to store all this stuff, and you're like, oh, now I want to remove it, do I get paid back for that?
Yeah, I mean, you're reducing load on the system.
I don't think so. But that's
Okay.
you could open maybe a call for that. But you're right.
I have a follow-up question on that.
Yeah.
But you couldn't delete things, right? Because is the output to a function part of the chain? Is that saved in the chain along with everything else?
You're talking about the persistent storage? So every
Yeah.
contract has a persistent storage with it.
Yeah.
And that's the expensive operation that you're paying for in gas, or you're paying to sort of store it. So he's saying, if I go and I delete my storage, do I get some gas back for that? Do I get some money back?
Oh, like if, for the next
I do it,
block.
like,
You're
in
not storing
5
more,
years
you're
or 2
deleting it. Yeah, I
years.
see.
You never actually reclaim the space, I guess. So that's the answer.
It's in the chain still, right?
Yeah.
So you talked about getting paid gas for running these contracts.
Yeah.
And what is there to verify that you're actually, like, say you claim when you put this thing on the network that it's going to cost X and it actually costs half X. When a miner is running this, what prevents them from just saying it costs the full amount, even though you claimed, like, when I ran it, it only cost half of that? Does that make sense? What prevents
I
them
think
from
so.
doing
I
that?
think because it's based on the steps. So the cost is, again, it's not arbitrary. It's deterministic in terms of the steps that it would compile down to. So you could run it and you could see, well, I guess depending on the state that you ran it against, but you could see how many steps it's going to take, right? And you're just saying that you're going to pay, for each step, you're going to pay this amount of gas, and you're willing to pay up to this amount. So you could calculate it before you submitted it, or get like a bound. Does that make sense?
Well, but if it's dependent on other state on the network when the contract is run, I can't verify it ahead of time.
Well, you could get close. Like if you knew when you submitted, this is a state of the most recent chain, unless something big happened, right? Then.
But is there any form of like verification at that point of time that the block is submitted, that like a miner successfully gets the hash, they've run everything on it, but they've claimed that they should be paid gas for everything on there at full price, even though it cost half for each of them? Is there anything preventing them from claiming full gas price?
I mean, that would probably be invalid because you would know the state of that block exactly that it was run against, right? So then if another miner was verifying that, I would assume that would be in the verification protocol,
So
where you could then say, no, this is the state of the block that you're working off, and you just charged it wrong. So that would be an invalid block. So maybe that wouldn't get added to the chain. Like if someone accepted that and they were going to validate it, much in the same sense as he was asking about the transactions, it wouldn't be a valid block, right?
But does that mean that verification requires running all of the contracts associated with that block to their end and counting all of the steps on that to see how much gas should have been consumed?
Yep.
Okay.
And that's what miners do, right? So miners are full nodes that do all of that. And to your point, they get huge. And I didn't want to go into it, but in the paper they also talk about like simple payment verification or light clients, right? So you have full miner nodes, but those can get huge. At the time of this paper, they were saying it's 25 gigs, but now it's like 125 gigs for the Bitcoin network, right? So, and the idea is that it could get to like terabytes, right? And then no one's going to be running that. So you need a way to also have light clients that can validate the state. That's kind of tangent because I didn't talk about it in this because it just seems like there's too much. But you do that with something called Merkel Trees that allow you to, like, I don't know if I want to get into it, but they're like authenticated data
Go ahead and get into it.
Right. So they're like authenticated data structures. So if you have the root of a Merkel tree, you're allowed to see like if every transaction in that tree is valid. So it basically is a binary tree where the leaf nodes are the actual data that's split up, and then you take a hash of the leaf node, and then you take the hash of the node next to it, and you add that in the parent. And then the parent and the sibling of that parent gets hashed, and it goes up the tree, and it goes, I think I had slides. I had a lot of slides. So it's like, timelines. I had to cut a lot of stuff out because like, it's just too much. So this is the Merkel tree, right? So this is what they talk about in the paper. Your key would actually be, a path on the tree, but like, this would be a hash. So you'd have your value here, you'd hash it here, you take these two, you'd hash it here, you take these two, hash it here. And so if you have this Merkel tree and you want to validate a transaction, you can do it in like a log n steps, if that makes sense. And this is for light clients. So he does talk about that in the paper a lot because it's really important that you are able to not run a full node. Right? Yeah?
I have a question.
Sure.
When you were describing the sort of, when you want to do a contract, you guesstimate, I need 1,000 computations at a price. Is there any kind of inherent danger that, let's say you do this contract and 10 years goes by and the price of Ethereum goes through the roof, and then that contract is run and it costs you an exorbitant amount of money due to the fluctuation of Ethereum?
Transactions are the only ones that have that gas price in them. And remember, transactions are what you send in at the beginning to get into the system. So you wouldn't be running a transaction in 10 years. You'd be running a new transaction in 10 years, right? And if the contract just sits there dormant, again, until it gets invoked by some outside trigger, right, which would be a transaction. It always has to start from a transaction, and then it enters the system, like this one, right? So in 10 years, it would be a new transaction, and you'd have to reconfigure your gas. And the computation steps are what happens with the path of that transaction, right? The transaction comes in here, it's doing computations in this contract. This contract isn't charged. It's this person that's charged that initiated the transaction. And as it goes in and does this, all those are wrapped up in the steps. Does that answer the question, Darren?
Sort of.
No, go ahead.
No, I mean,
or you can talk about it at beers. Okay.
So the contracts are written with this EVM, and every code has bugs. So is there a way to invalidate a contract? Just say, I don't want to use it anymore, or anybody else cannot invoke it if they know about the bugs?
No, there's no bugs in Ethereum. That's obvious.
I think that's the DAO question. If you want to address what happened to the DAO.
So you're allowed to, you can set up your contracts in such a way that you could kill them. So that's the right way to write them, is have a function that you could call or a message you could pass that say, if I'm the owner, I can kill this thing and delete it. And to your point, that would clean it up or destroy it. And that's what you're supposed to do. You're always supposed to add a way to self-destruct or kill the contract if you're writing a nice contract, if you're a good citizen.
Is it obvious when you initiate all of the knock-on effects that are going to transpire? So you say, I only meant to get this part of it done, but these other parts come along. It's kind of like you log in and it starts downloading stuff to backfill your stuff. And you're like, I didn't want to do all that. But you have to pay for it anyway. Is that just what happens? You just didn't know you were going to pay for it, but you wind up paying for it because you wanted to get one thing, but this all comes with it?
Yeah, I mean, so that might happen, but you have that start gas price, right? So, I don't know what it is. So you say how much you're willing to pay, right?
Well, I guess what I'm asking is it apparent to you that by asking for this thing to happen, that you see this snowball start rolling away and all this is going to be charged to you. Is that apparent to you when you start? Are you completely read in? Like
Yeah.
it's up to you to just sign off on that and say, this is going to cost all this because, I mean, I know how much I'm going to offer, but but I'm not necessarily clear on how much it's going to cost me.
Right. So remember that all the node is, or all the state is like inside the system, so you have access to all that. So if you're running against block, I don't know, 5,000 or whatever, wherever your state is at that time, you see all the state in that block. So you could run it against that contract and see exactly what's going to get called, right? You're not doing like REST calls that go out to the world and do something. It's like all inside of each node that has its own copy of local state, right?
So you could pre-calculate.
You could pre-calculate, exactly.
And then you say, oh, by the time I'm done, this is going to cost me $750. Okay.
Yeah.
I guess I'll do it.
Yeah, exactly. And to the point back there, maybe state changes a little bit by the time your transaction goes through or whatever, but it's not going to be a lot most likely, right? Like maybe someone updated something. It depends.
I have a quick question. This sort of bounces off of Darren's actually. So in an early, let's say for example you have an early contract that was very, very price. It was, it would take a lot of gas to run, but you didn't care when you wrote it because Ethereum was very, very cheap at that point.
Yeah.
It's possible for programs to get priced out of usefulness in this system, isn't it? Like, and if the price of Ethereum keeps rising,
Yeah.
a program written early on you could come back and say, well, that was a useful thing, but I no longer want to like it. The benefit I get from running it is no longer, reflected in the cost, right? So that's just a kind of a built into the system. It's just a thing that happens.
You mean like the bytecode to run that contract was like written poorly or like written in a way that now it becomes inefficiently? Yeah. So then I guess you could kill the contract, but then people calling it would have to know that, right? Because the contract's always going to live there. You could kill that contract if you had it and deploy a new one.
So I mean, this follows off of both this whole conversation. So you could effectively do like a limit order within the contract. You could basically pre-calculate it on the block and say, oh, this is going to be too expensive. Nah. You could be like, I only want to spend this amount to do this contract. I'm going to pre-calculate on this block and be like, no, it's too expensive. Just don't do it.
In the contract?
Yeah.
So it goes back to the point there that like the contract isn't the one that cares about the gas, it's that transactor. So you as an outside person coming in that's going to start that chain reaction that's going to start invoking contracts, you care about that because that's coming from your account, right? And you're the one that's submitting that gas. You're the one saying, I think it's going to take this many computation steps, and I'm willing to pay this much. And I can see the whole state of the world, so I can see all the other contracts that are existing. And remember, this is more of a deterministic world, so it's not open, so they're not like updating and doing these different things where it like changes under you. You basically can see the state of the whole world, and you could run against that.
Okay, so me, the transactor, like I can write a contract in such a way that it can alert me, like it's going to be too expensive, don't do it, and like then I just kind of don't do it. Sort of.
You could write a contract, and
Well, I guess I'm getting a little confused with the transactor and the contractor kind of.
Yeah, I think that is confusing. So again, transactions are only sent from an account, and it's the first thing that starts. And you'll always have access to this transaction ID from inside any of these contracts, but this person doing this is the one that's paying for it, right? This contract doesn't pay for it. The contract is just doing code, doing steps. But because you called that contract, you have to know what that contract's going to do. You're going to pay for it. And then you're going to pay for this contract too, and that's invoked. And you're going to pay for this contract too, and that. And so you're going to pay for the whole chain that your transaction sets off.
Can you do a dry run without committing and without spending any gas?
Yeah.
So you can say, okay, the contract would cost me this much gas, and you hope that in 2 seconds when you do it live, it's going to cost you that much gas.
Do live. Yeah. Exactly. Yeah.
All right, go ahead.
But to do that dry run, wouldn't you have to have a complete node?
You have to have a snapshot of what you believe to be the state of the system.
Okay.
Or you could have just what you're interacting with, right? So again, you don't need everybody's state. You just need the state of the contracts that you're actually going to be invoking.
I'm sure there's tools.
There are many tools. Again, DAppHub is one that I like, but yeah.
Well, let me ask this question while they're turning that one on. So I heard that CryptoKitties ground Ethereum to a halt. Can you explain how that happened?
A lot of cats. I don't know. No one can explain that, right? What are CryptoKitties? I don't know. But like, there's a lot of transactions that were coming in doing overwhelm the network, and to that point, like the Ethereum community works on different things. So they're even looking at different types of consensus mechanisms, like proof of stake and different things. But the idea of this paper basically is let's abstract that away from you as a contract writer, so you don't have to worry about that. We can keep updating this blockchain decentralized consensus mechanism that we're running on, and all you have to worry about is we'll take care of this. You be creative, you write a contract, that's it, it'll be deployed.
So as far as contracts go, is it assumed that contracts can get run multiple times? Like when you're designing a contract, you have to make it safe to run multiple times because multiple miners might grab it, try to do it, and they get credit for it?
What do you mean by that?
Well, I guess it's kind of like, when you're mining a block,
Yeah.
right? Multiple guys might mine it, but only one of them is going to get credit for it, and the other one did a bunch of garbage work, but whatever. Is it similar apply to contracts? They're like, oh, as a contract, I'll do it. And someone says, I'll do it. And then like a whole bunch of miners go out and try to do this contract, but only one of them gets credit for it. And then when you design a contract, you have to make it so that it can be run multiple times. And then kind of follow up, it's like, how do you validate the contract was done correctly? I guess
the contract could be run multiple times. Is that what I mean? Like,
yeah, okay, so I want to confirm that you have to, when you design a contract, it has to be okay. It has to be okay if this code is run multiple times.
Sure.
And it's not going to have some sort of side effects.
Transaction can be run by multiple miners.
A transaction or a contract? I think he's asking about contracts.
Specifically
he's asking
contracts.
about the code that's deployed. So
Right.
it would be run multiple times because everyone's going to run that, right?
Right.
Again, it's a closed universe, so we're all going, if we're miners, we're all going to get a copy of that contract, and we're all going to run it. So you're going to say this, that, but we can all run it to verify it, right? And it's going to, just because we all have I have my own local copy of the state, I have my own local copy of the storage, I have my own local copy of the code. It's like, I'm not doing I/O, I'm not doing randomness. That's what we're coming to consensus over, is the state of the world, which consists of that, the internal and the external accounts, all the storage, we all have that. So I could run as one node and I could do it, or I could run as many nodes. So when you're green, when you're coming to consensus in that block, you're saying, this is the new state of the world, then you run it again, and then everyone runs it. That's fine. So it has to be run multiple times. Does that make sense?
Yeah, so just like in Bitcoin, you're saying that you're making sure the transactions are all correct, yada, yada. This is just, you have transactions, now you also have the contracts, just another thing that gets kind of meshed into that block on top of everything else, which again, when it gets validated and it's good to go, they're actually checking again, this is all correct.
Exactly. And that's what that's why it allows for arbitrary state transitions, and the state transition isn't just value from one account to another, but also this information and changing the storage and this type of thing. But go ahead. Yes.
So you have to be very careful not to have side effects though from contracts, right? When you design the contract.
Yeah, like what kind? So again, it's deterministic. So it's like a different universe, right? So you won't have I/O. You can't write something. You can't get randomness out of anywhere. So like otherwise that wouldn't be replicated. You wouldn't be able to execute the same contract in your node and my node if we could just get randomness, right? So that randomness also has to be deterministic. They do mention that you might be able to use like the nonce of the block because you wouldn't know what that was ahead of time as a type of randomness, but you can't just generate something out of nothing. Everything has to come in through the contracts, and then once it's in that closed world, everything exists in that closed world, and we all get a copy of that closed world. Okay. Make sense? Functional-ish programming.
Hi, I just had a quick question. You see a lot of private companies taking the Ethereum public code base and basically forking it for permission networks. Are you excited about any potential contributions that are coming out of those projects back to the public code base? Because they talk a lot about, we've got an Ethereum community that's continually building on the public code base that's going to help us. Do you see anything on the inverse? Is there anything that excites you from what you're seeing from private companies back to the public code base?
Like Quorum? So Quorum's a project out of JP Morgan that's a fork of the Ethereum codebase that allows for private contracts or sort of state channels between entities. So that's interesting. Applications between organizations where they can do these types of things, I guess, between organizations. So yeah, you can fork and take that to and there's different consensus mechanisms and things that you could plug into it. So there's a lot of explosion in this space just in terms of you have a blockchain, now you have this idea, you have both in the public and the private space people doing different kinds of chains, like our chain, like Quorum, which is again JP Morgan, fork of the Ethereum code base that layers privacy on top of it. And yeah, I think it's just cool that everyone's trying out these different ideas and leveraging, yeah.
So you mentioned that the way that you put more information into kind of the Ethereum universe is via this contract. How do you inject information like after the fact if I'm running like a fantasy football league or a lottery and I don't know who the winner is a priori? How do you take information that's not in the universe and supply it to the EVM?
Right, so that was sort of the Oracle thing that I probably talked through really fast, but that's fine. So that's bringing information from outside world inside. So you'd have a contract that sits there that says, I want fantasy football stats or whatever you're talking about, right? And then that would accept a transaction. So you'd have some sort of ticker or something that would be initiating a transaction. So it would have to have an account, and it would have to do this whole gas thing and send a transaction in. But then it would update that contract, and that contract holds its own state. So then you'd send in that information, it updates the state, and then other contracts can query that contract. Does that make sense? Because now you've got that state into the closed world. Let me know if that makes sense. You look like
no, it does make sense, but how do you control for like people hijacking? Like if someone else wanted to say, I just want the lottery.
Right, so how do you make sure that's a trusted source that's going in? Yeah. So you have to make sure that's a trusted source. So that could be you. No, I mean like so there's ways to do that. Well, you write it in the contract. So you have the transaction sender. That could be you, and you're like, I'm the trusted source for my contract, so I will only accept an update if it comes from this account. And then you have just a guard on the function that says, if it's coming from this account, accept it, else don't, right? And in the paper, he talks about different things like shelling coins or ways you'd have different people calling in if you were looking for something like this type of contract where you want a bunch of people to call in and give some information, and the people that give the right information get paid, but if someone lies, they don't get paid, and the only way everyone can agree is if everyone's honest, because otherwise you can't guess what you're going to do, right?
More questions.
One right here, sorry. Libby, do you, are you optimistic about, are you optimistic about universal basic income for every human being on the planet in a couple of generations if we don't blow ourselves up?
That's not loaded.
Well, I'm excited that people are trying it out for sure, and I think that they need things like identity, and I think it's a big problem, and obviously we see growing inequality, and it's all over the world, right? So I think I want to be optimistic about it, sure. Like why not try it out? You have to try it out, and I think of course you can be negative about everything and say it's never going to work, people are going to do this, it's going to get gamed, but if you don't try it out, you'll never know. So I like the idea of the sort of Ethereum idea of let's just try it out, right? Yeah, right? That's Chaplin is like my favorite ever.
Libby, there was a question, there was a slide with a panda who was...
There's a lot of panda, I think,
who was sending...
Here's like my
yes,
go-to thing. This
yes.
one? Okay.
Question is, who is this panda? Is this like... is this like an end user, or is this like a
developer? I thought you meant the identity of the panda, and I was like, I can't tell you that. But this would be an end user. So this would be somebody that has an account in Ethereum, and then they have a private key, right? So when you have an account in Ethereum, like Bitcoin, it's a private-public key pair. Your public key is what tells where your account is in the network. Everyone can see that, or it's a hash of your public key. And your private key is what you sign a transaction with to say, I own that account, right? So you can sign that as many times as you want, and everyone can publicly verify that you do own that account, right? So Panda has a private key and has an account inside of Ethereum that's a public key.
So just a follow-up question. Yeah. If somebody designed a contract, right, and it's a developer, and this is like own token system, would this Panda still be end user, or would it be like a call on a back end of that person who actually developed the contract?
No, Panda wouldn't be a backend. So Panda would be a user that's starting that transaction that is then sending a message to a contract to invoke the contract, or maybe transfer in value or something. Or there's another type of contract or another type of transaction that can create a contract initially, right? So Panda can create a contract, with a transaction, or Panda can send messages to other contracts, which can then do this whole chain thing, right? Call another contract, call another contract. But Panda will always be the owner, will always be the initiating transaction ID for that chain. So even if you were in this contract on the EVM, you could say, oh, can you give me the transaction ID of the owner? And it will be this Panda, no matter how deep it goes. Panda always owns it.
Question, right?
Feedback, I think. Hi, I had a question about executing contacts multiple times. I think it's related to what somebody else asked, but I didn't really get it, right? So let's say we have a contract, let's say we bet on a horse race, right? The horse race is gonna be in a week from now, and if horse Rusty wins, then you have to pay me 10 Ether, otherwise I have to pay you 10 Ether, right? And that's what the contract says. And now we introduce this contract into the network, and now a week passes, the race happens, and Rusty wins, so you owe me 10 Ether, right? And as I understand it, the way that I get that 10 Ether is that I send a transaction that says, run this contract, right? And then the network runs the contract, and it takes 10 Ether from your wallet and transfers it to mine. And now my question is, what's preventing me from sending another transaction, asking the contract to be run again, in which case I would get 20 Ether from you? Does that make sense?
Yeah, I mean, that's what you write into the code, right? So you could have a flag, has this been run yet? Or you have a map or something like that, right? That when you come in and you check it, if you pay out to that person, you only do it once. That's how you'd write your code, right?
So
keep track of that.
So these contacts are allowed to kind of maintain states in perpetuity on this network? Okay.
So they have, every contract has its own storage that only that contract can access. Right? So that's what you get. That's why I said it's kind of like Lambdas plus storage. So the storage is connected to every contract. So yeah, you can keep maps in there, you can keep state, you can just write basically like arbitrary programs.
Okay, so the state is not only maintained while the contract is running, it's also saved for later, right?
So there's a volatile state that would be sort of the stack or the memory when you're executing it, and then there's permanent storage state that we were talking about before of like, what happens if we store tons of data? Can we delete it later and then get our money back? No. But you can store arbitrary state, but you pay for that.
So you said the contracts run in this closed environment and they are not allowed to access any outside information, and there can be no randomness that is involved. So what stops that from happening? Like if I were to use, say, the time that this contract is running in as a part of the logic inside the smart contract,
you don't have access. Like you wouldn't have access to time. You could have access to a timestamp on the header.
Okay, so like it's just impossible to have randomness of any sort written into the program.
Yeah, exactly.
So that's the only thing that is stopping me from having randomness. It's not like if I write something and it's just rejected or something.
Right, yeah, because you can't have randomness, so the EVM wouldn't let you do something that was random because it wouldn't support that operation.
Oh, okay. Thank you.
Looks like I'm close.
Hey, maybe a little bit not related to the paper, but still, what is the biggest issue you see with Ethereum/blockchain, and maybe why do you think so, real quickly?
Me?
Yeah.
I'm not an expert. What's the biggest issue with Ethereum/blockchain? Brian? What's the biggest issue with Ethereum/blockchain?
What's your answer?
Like sharding and the CryptoKitty thing that you're talking about, where like sometimes the network gets overwhelmed, but they're working on things for that, like sharding and different consensus mechanisms. The other one you hear about a lot is proof of work taking a lot of energy, right? So that's a common theme. They're also working on things with that to try different types of decentralized consensus mechanisms. But that would sort of be the idea is like, as a contract writer, don't worry about that. Like, let's build that platform for you that's too low level. And let's empower people to write these more creative things to focus on different decentralized smart contracts or decentralized applications that can potentially do things like UBI or whatever, right? Like, let's try to do that. But.
Or if P equals NP, then all this is...
PapersWeLove coins, like very important, and I'll get you one this weekend.
Yeah. If P equals NP, though, we're all doomed, so...
One more question. I think we'll do this the last one. Last question.
It seems there's a lot of things that you have to get right in your contract. Like a lot of things could happen that could make you say lose money or something like dumb mistakes that you're not accept or you're
Again, no bugs, right? We already went over that.
right, but you're writing the contract, right? Like
I'm
me,
kidding,
as a person writing contracts. So is there like any sort of framework that prevents you from doing these kinds of newbie mistakes? Like, or does everyone have to get their contract logic and vulnerability sort of handling right the first time? Or how do you prevent a lot of these mistakes that people could potentially make?
So again, I mentioned DAPHub, which I like a lot, but they do developer tools for Ethereum. And so like you can use those tools and you can like run a test network locally so you can get state, and then you would like, you wouldn't execute the contract right away on the mainnet, right? So mainnet would be the one that is actually going to charge you that you'd need an account with. You can run a whole copy locally and then check it out there. And then there's also public test nets that you could run against. So you wouldn't just be like, okay, oh, this works, push the button, and then oops. So you have, and that's part of what's going on now, is trying to build that ecosystem, I think, and really focus on like developer tools and try to make it so that we have more, that there are more things that help developers cut. I thought cut.
All right. Thank you so much. Let's give it one more time.
Thank you.